video is for example 1 on your extension for Unit 8, horizontal stretching and compressing of quadratics. So it's similar to the vertical stretch and compress, but this time we're working the x's horizontally instead of the y's vertically. So we have a graph over here already made for you, x squared minus 4. That is written right here. So here's what we're going to do. We're actually going to use your calculator to help us see the change that's happening, and then we'll talk about the rule. So it says we have f of x here. We're going to label it as f of x. That's our starting function. And it says consider a new function g of x, and I'm going to highlight it in pink. I think we can see it. Yeah. So I'm going to use pink over on the grid, so I'm going to keep the colors together. Consider that function. Use your calculator to graph it. So we're going to graph the quantity 2x squared minus 4. So on your calculator, we're going to go to y equals 2x squared minus 4. Okay? So it looks like this. And I'm going to make a table so we can plot some points. And let's see which points are going to fit on our grid. It looks like negative 212. I don't think that'll fit here. No. But we can make negative 1, 0 fit. This point is here. The next point that fits would be 0, negative 4. I was going to use pink, wasn't it? Negative 1, 0, 0, negative 4, and 1, 0. And that's it, because 212 would be way up high. And let me just make sure, let's show you that it's the same. So we started with the graph x squared minus 4. So I'll type this guy underneath here. And then we'll see right away that we did end up graphing it right, because it's going to be skinnier. So let's look at our picture. When I connect those dots, oops, that is not a good line. Let's try that again. Start way up here, come down to the vertex, back up. And this graph, I'm going to label it, that's g of x. Now, how does that graph look different than the parent function? I would say it's skinnier or more narrow. So it is skinnier. We'll formalize that in a second. This graph looks smaller and more narrow. All right, now we're going to consider a new function, 1/2 x, the quantity squared, minus 4. So I'm just going to change the top equation here in my y equals. So I'm going to change that 2 here to a 1/2. Delete that 2 and hit graph. Now that's the blue graph, and the red is my original. So this blue graph looks wider. Let's make the graph here on our paper. So I'm looking at just the blue. Okay, so let's do the whole numbers. I'll have negative 6, 5. Yeah, that'll fit. Negative 6, 5. So I'm going to use green here. All this in green. So negative 6, 5. What else works? Negative 4, 0. I can erase the second one if it's confusing you. Negative 4, 0. Negative 2, negative 3. We're going to have to keep scrolling. So it looks like 0, negative 4. Vertex again. And then we're going to have some symmetry. So I can, if you want, you can look at your table, but we're going to have some symmetry here. So 2, negative 2, 3, 4, 0, and 6, 5. You know how symmetry works on these parabolas. And we're going to go down and trace the dots. And that is going to be the graph of h of x. And that green graph, compared to our parent function, it is wider. Now, what stayed constant and what changed and how did it change? Well, it looks like the vertex was constant, right? So the vertex did not change. And that's really only because we did not move the graph up and down or left and right. We kept it with a -4 every time, so always shifted down 4. We didn't adjust it from there. Well, let's take a look here. Can't see these points right here, but you can see that they're all on the y value of -3. And all of these points are on the y value of 0. And all these points are at the y value of 5. And those were all points that were on my parent function, the same y value. But what changed about them? Well, I guess I'll add this here. The vertex did not change, or the y coordinate of any point. So all the y values stayed the same. What changed was the x value. So if my parent function had the x value of 1 right here, it went in or it went out to 2. This y value or x value of 2 went into 1 and out to 4. So the x coordinates changed. Now let's talk about by how much they changed. If I look at this first one, this pink graph, so I'm going in from 2 here to 1 for my x's on those 2 points. I'll use the highlighter here. Going from 2 here to 1. Well, 2 to 1 or 3 to, it looks like about 1.5-ish is half as much. So here the x values got half as large, or smaller by half, or something like that. They got smaller by a factor of 2. If I look at the green graph, and I look at those same points, here's my highlighter. If I start at 2 here, ooh, that made a black part. Start at 2, the x value out here went to 4. This, I'll do this side, this -3x went to -6. So on my green graph, the x values got 2 times larger, not half as big, right? So it went narrower by half, and this one got 2 times as large. Well, that shows us a kind of odd feature for these graphs, for horizontal stretches and compressions, or horizontal dilations. It's kind of tricky. If I have a function where there is a number inside the parentheses right in front of the x, okay, so what that would be is like our graph, 2x squared in the parentheses. You're going to have a horizontal stretch, which means you're getting wider if the value of c is in between 0 and 1. So that means if it's between 0 and 1, and it is a fraction that's less than 1. So something like 1/2, 2/3, 1/5, something like that would be a horizontal stretch, which seems a little bit odd. We're going to have a compression, which means you get narrower or more narrow if the value of c, that number in there, is bigger than 1, 2, 5/2, 3, right? So let's add that to our rule chart. Okay? So here's our rule chart. It's going to be the bottom 2. So we have, I didn't fill in the vertical stuff here, because I'm making this before I taught it. So vertical here, we know if the number out in front, if the absolute value is bigger than 1, that is a vertical stretch, IC. And if the value is in between 0 and 1, you'll have a vertical compression. This should already be on your chart. All right, so vertical compressions are the ones that make sense. They are straightforward. If the number is bigger than 1, it's a vertical stretch. If it's between 0 and 1, it's a vertical compression. Horizontal is the opposite. Everything that happens inside your parentheses, left and right, horizontal stretch compressions, is opposite of what you expect to happen. So if my number, like a 2 right here, 2 is bigger than 1, so I expect it to get bigger. It's not going to. This is the horizontal compression. Now, it's a horizontal compression by the reciprocal of that number. So it's a horizontal compression by, I'm going to say 1 over c. Or in my example, that'd be by 1/2. So if I see a 2 there, that's horizontal compression by its reciprocal, which is 1/2. If I have a number smaller than 1, between 0 and 1, that is a horizontal stretch by the reciprocal of c, 1 over c. Now here, the reciprocal of 1/3 is 3. Okay, so we are going to spend some time. It's kind of confusing. The rule itself you can probably remember after you do a couple. The graphing is going to be hard, so we're going to take this one example at a time. So you're going to go back to the module, and you'll click on example 2 to move on.